Okay, in this segment, I want to finish off a couple of things related to the frequency response of the Mirror-Cascode amplifier that we were talking about last time. So and I want to compare this in particular to the frequency response of the current mirrored diff amp. So we're going to assume that there's some output load capacitance on both of the circuits. And so just sketching up here the circuit, the Mirror-Cascode circuit. What we're talking about is a diff pair, our two current mirrors. We have cascode transistors in the output branch. We've got a VCN here and a VCP here. And so to the circuit, we're talking about adding an output capacitance, C out. And if you take what we did last time and you apply to it the same kind of ideas that we developed with the current mirror amplifier when we put the capacitor on the output node, what we would find is that the GM of the circuit is exactly as it was before when we hold the output voltage fixed. And then the R out, or the Z out of the circuit, would be the Z out of the cascoded output branch, like we had before, in parallel with 1 over j omega C out. Right? So we could imagine splitting the output into two pieces, one connected to the output of the amplifier, the output branch of the amplifier like we had before, and the second branch being that capacitor all by itself. And we would find the original output resistance, incremental output resistance of the amplifier that we calculated last time, and then we'd have the 1 over j omega C out in parallel with it. And so the differential mode gain, which is dV out dVn, or dV dm, would be equal to the GM of the diff pair transistors, GMN, times GSN RON squared parallel GSP ROP squared. And that would be in parallel with one over j omega C out. And so what I'd like to do with this is basically to recognize that we can distribute the GMN, a constant, through the parallel operator here. And so this is equal to GMN GSN RON squared parallel GSP ROP squared in parallel with 1 over, or actually GMN over j omega C out. And we could expand this out as product over the sum and factor out the constant term, and we would have, or use the 1 over j omega C out upstairs to clear out the nested fraction and do it out. But I want to try something a little bit different with this to illustrate something which I think is a fairly important concept here when we're dealing with frequency responses. And that is, I've got a parallel combination. Right, so I've kept this group together because this was our original low frequency gain, A0. Right, and that's frequency independent. And it was positive, non-inverting. And so I could imagine plotting on a Bodhi plot. Actually, why don't I color code these things? We'll see how this color coding comes out on this. I'm going to call this, oh, that marker is terrible. Call this A0. And we're going to plot this one in blue. Okay, so on the Bodhi plot, we have here, oh, this marker is not what I wanted. We have here magnitude of ADM in dBs versus omega. I'll call this the magnitude of A. Then we have the angle of A. And so let's plot these two components, the blue one and the red one, as a function of frequency on the Bodhi plot here. So A0 is some high gain up here that's constant at all frequencies and has a phase angle of 0 degrees. It's a positive real number. And so it's got some magnitude expressed in dBs and 0 frequency. Now the blue component here is falling inversely with omega at all frequencies. And that means that it's a straight line with a slope of minus 20 dB per decade, minus 20 dBs per decade. So the slope is minus 20 dB per decade. And you'll notice that we can actually pin down where this crosses the 0 dB line. Okay. And that is where the magnitude of this component becomes 1. Right? And so the magnitude of this component becomes 1 precisely when omega is equal to GM over C out. Which we could call omega 1, the unity gain crossover frequency, which is GMN over C out. Okay, that pins down this line. Right, so that's a feature of this line where it crosses over the 0 dB line that we can pin down. And of course, the phase angle of this, since it's actually pure imaginary, right? So if we multiply by j over j, we would get minus 1 from the j squared downstairs, and we'd have a j up in the numerator. So it's got a phase angle of minus 90 at all frequencies. Okay? And so the question is, ADM is the parallel combination of these two components that we've plotted separately on the Bode plot. What do we know about the parallel operator? Right, we said that the parallel operator is dominated by whichever component that we're combining in parallel is the least. Okay? Well, at low frequencies, obviously this constant gain, even though it's large, this A naught, even though it's large, is going to be much smaller than the impedance of this, or this impedance of this capacitor times GMN, which is approaching infinity as the frequency goes to 0. And so that A0 will dominate in the parallel combination. And so the behavior of ADM is going to follow the behavior of A naught. And actually the phase is also going to follow the phase of the dominant component. It's going to be 0 degrees at low frequencies. Well, after this place where the blue line crosses the red line, very rapidly, the blue line is going to become much less than the red line. And A0 will follow the blue line, or ADM will follow the blue line. And it will also follow the phase behavior of the blue line. And what it turns out it's going to do is basically make an ordinary sort of 3 dB corner down here. It's going to transition smoothly between the two. And the phase is going to go smoothly also between the two. And it's going to go through minus 45 at this corner frequency. And notice we can actually solve for the frequency that makes the magnitude of these two components equal to each other. Okay? So if we set the magnitudes of these two things equal to each other, so the magnitudes here are G, GMN, GSN, RON squared, parallel GSP, ROP squared, equal to the magnitude of this one, which is GMN over omega C out. If we solve for the omega, we move the omega upstairs here, we move this downstairs here, we get omega equals GMN over GMN times GSN RON squared parallel GSP ROP squared C out. And the GMNs cancel, and we're left with 1 over GSN RON squared parallel GSP ROP squared C out as 1 over tau, as we've drawn 1 over tau here in this diagram here. And you can check this out on your own if you like, but if you expand this out as the product over the sum, you will find exactly that you get a low pass, first order low pass type response with a low frequency gain, precisely of this A0, and you'll find that this is indeed the corner frequency that you get by doing the algebra. And so this is actually a nice way of dealing with complicated frequency response calculations without having to do a lot of the algebra. If you have a parallel combination, you can basically deal with the components of the parallel combination by plotting them separately on the Bode plot, recognizing that we have a double log scale here, and so very rapidly, if one curve is above another curve, it becomes much larger very quickly. And so we have this this way of dealing with these things and finding where the pole frequencies are, where the zero frequencies are, just by sort of setting the magnitudes of these things equal to each other to find out where the crossing points are. Okay. Now, another thing I wanted to bring out with this example is if we go back to our discussion of just the mirror, the current mirror diff amp, we could have said exactly the same thing. The only difference was that we had multiplied the RON by the GSN RON and the ROP by the GSP ROP here. And so this term, this blue term, would have been the same for the current mirror diff amp. And so this blue curve is basically invariant for this amplifier architecture given a particular value of Cout and a particular bias current, which is going to set the GM of the diff pair. That's going to set the GMN. And so what that says is that using this cascoding technique, we've boosted the gain up, we've moved the A0 up, and that's basically shifted this low frequency corner back proportionally to the amount by which we've increased the gain. Or if you look back to see where the corner frequency was for the current mirror diff amp, the corner frequency 1 over tau was just RON parallel ROP times Cout. That was a time constant, so 1 over that would be the corner frequency. And so by increasing the gain by cascoding, we haven't made the amplifier any faster. We've just basically pushed the corner frequency to lower frequencies. And so that's the other thing I wanted to bring out with this idea here. Okay. One other thing that I wanted to say about the current mirror, the Mirror-Cascode diff amp. I forgot my diode connection here. Oops. I do that too sometimes, don't I? Anyway, I wanted to say one more thing about the Mirror-Cascode diff amp. This is kind of the most simplified version of the circuit. And in practice, if we wanted to use a circuit like this, we probably could not get away with just putting the cascode transistors in this output branch. We would probably also, for the sake of sort of symmetry and making the response of the circuit less prone to offset, we would probably need to cascode this PMOS transistor, and we could use the same cascode bias voltage here, VCP. So now we've basically done the same thing to the current mirrors in both paths around the circuit. Okay, so up to this point, the circuit is highly symmetric. Okay, we would probably also want to do something a little fancier down here with this NMOS current mirror. We would probably want to add a cascode transistor on the input branch as well, VCN, and then basically make our diode connection around the cascode transistor on the input branch. This current mirror is one of several sort of fancy current mirrors that have very, very high performance And this particular one is called a high swing or low voltage cascode current mirror. It has basically the input voltage requirement of a simple current mirror. It's basically one diode drop as the input voltage above ground. And if we bias the cascode properly so that this node and also this other node here wind up being about 1 VDS sat above ground, then we have a very, very wide output swing. The output voltage here can get within basically about 2 saturation voltages of the ground rail, and we maintain a very, very high output resistance. So this is a very, very good current source. And so with the addition of this cascode transistor on this internal branch, PMOS cascode, and making this simple current mirror into a high swing or low voltage cascode current mirror, this amplifier would be a very, very nice single stage amplifier with a gain of in the range of like 80 to 90 dBs pretty easily. Okay, so that's all I wanted to say about the Mirror-Cascode diff amp. I may talk a little bit about generating cascode bias voltages. At the very least, I could probably give you guys a short paper that I wrote on a low voltage cascode bias circuit, which follows nicely from the things we've been talking about this semester. But I think in the remainder of this segment, what I want to do is to try to go through the heuristic that I use in deciding where to take into account the early effect when I'm doing these kind of small signal or incremental analyses of transistor circuits. So I mentioned that. So how to decide where to model early effect. Okay, this is going to be a heuristic. And the basic idea I want to illustrate with our 5 transistor diff amp. Okay, and the first thing to note is that where you need to account for the early effect may depend on what part of the calculation you're talking about. So you have to be sensitive to, you know, what are the conditions under which you are doing a calculation. Okay, So for the differential mode gain calculation for this circuit, there were basically two phases of the calculation by node fixing. One was the transconductance gain of the circuit under the conditions of the output voltages being held fixed by an ideal voltage source. Okay, so during that phase, the output being held fixed by an ideal voltage source is part of the deal. And then the second phase of the calculation is calculating the incremental output resistance of the circuit. And in that case, the output voltage being held fixed by a voltage source is not actually an inherent part of the deal. Okay, now we do use that voltage source conveniently to actually do the calculation, but actually what we are probing in that particular case is the incremental output conductance of the circuit. Okay, and that's actually different than the incremental output resistance of the circuit, where formally the excitation signal would be a current source excitation, and the response of the circuit would be the output voltage change. Okay, we can actually do the calculation the other way, but for the purposes of deciding whether or not the early effect is significant in a given place, we actually have to think about using the current source excitation as sort of the baseline condition for the calculation. But the idea is that if we're going to consider, do I need to put the early effect in a particular place? Let's start out with let's start out considering MB, the bias transistor. So what we're doing here is we're taking a port that is coming out of the circuit, which is in this case the source and drain of the bias transistor. And what we're saying is we're thinking about, do we need to stick ROB here? On that port. And the question that we're asking effectively is, what is the input resistance seen looking into that port compared to ROB? So if ROB is much less than Rin, then we need to include ROB. If ROB is much greater than Rin, or said another way, Rin is much less than ROB, then we don't need to include ROB. Okay, so this is effectively being connected in parallel with the rest of the circuit. Not just the transistor, but also the other stuff that's connected to the transistor. And so if the transistor plus all the stuff that it's connected to renders the impedance seen looking into this port here so small that ROB would be negligible in parallel with it, then we don't need to include the ROB. Okay, now if they're on a par with each other, if they're about equal to each other, then you should include the ROB. Okay, but if you have this condition, then it's probably safe to neglect the ROB in a given location. And so what I typically do is I move around the circuit in my mind without actually explicitly doing the calculation that I'm going to step through here. But that's the kind of heuristic that I'm using when I decide whether I need to take into account the early effects. So what do we do when we compute, and let's assume that we're in the GM phase of the calculation, so the output voltage is held fixed here. Well, to calculate the input resistance of a port, what we do is we hang a current source off of it. We inject a current into that port, and we say, what is the change in voltage? that results across the port. And Rn is equal to delta Vn over delta In. Right, and so a convenient way of doing this is current source splitting and superposition. And so we would split the delta In into two replica sources. And then ground this intermediate node. This is source 1, let's say, and source 2. And we open up, let's say, source 2, turning off source 2, considering the change in the voltage across the transistor here due to replica source 1. So delta V in 1 would equal delta V1 minus 0. This side, notice, is connected to ground, right? So that side is 0, so it's just delta V1. Well, all right, we're injecting a current in here. We see the drain of MB, right? So that's an infinite incremental resistance. And we see the source conductance of M1 and the source conductance of M2. So we see 1 over GS1 in parallel with 1 over GS2, which is 1 over 2 GSN. So delta V1 is going to be basically delta In divided by 2GSN, say 2GS1, GS1 equals GS2, and then that's it for the delta Vn. Due to replica source 1, we move on to replica source 2. So we're sucking a delta In this case from the ground terminal. We're not going to move the ground terminal. We're not changing anything else in the circuit by doing that. And so delta Vn2 is equal to 0. And so delta Vn is delta Vn1 plus delta Vn2, which is equal to delta In divided by 1 over, or divided by 2 GS1. And so Rn is equal to 1 over 2 delta Vn divided by delta In. That's equal to 1 over 2 GS1. And that's going to be much less than ROB because GS and RON is much bigger than 1. And so if we move the GS1 up here, we get 1 over 2. And so if it's much bigger than 1, it's also much bigger than a half. And so we can move on to a different transistor. So if we think about, say, moving on to transistor M1, where we put our delta In here. And our Vn plus delta Vn is the voltage now between the drain and the source of M1. We split the source. Ground the intermediate node. 1, 2. Delta In, delta In. Well, in this case, delta Vn is equal to delta V3 minus delta V. And so when we turn off replica source 2, by replacing it with an open, we're thinking about injecting a current onto node V3. And so we have to think about what that's going to do. Well, it's going to move V3 by some delta V3, and we can call this V31, right? The component of delta V3 due to the change in replica source 1. And that's going to be given by just the 1 over GM3, right? And so that's going to be mirrored here. That's going to go into this current mirror, delta V, or delta IN rather. It's going to be mirrored by M4. And that's going to be supplied by the output voltage source. Right, so it's not going to affect the node V at all. We're injecting current into this current mirror. The current mirror is mirroring the incremental current, and the output voltage source is supplying that. And so the delta V in 1 is just going to be delta V31, which is just going to equal delta IN over GM3. And so then we move on to replica source 2. Here we're going to suck delta in out of replica source 2. Well, that's going to move delta V, so there's going to be a delta V2 here, and there's going to be a delta V3 too. Right, so that current is going to come from partially from M1 source and partially from M2 source. And because it's balanced, half of it will come from both places. So this will be delta IN over 2, and this will be delta IN over 2. This delta IN over 2 is going to, again, come from the output voltage source. Right, this delta IN over 2 is going to be mirrored by M3. And it's going to be mirrored by M4. And actually that delta IN over 2 will supply this delta IN over 2. And so we actually won't have to have any voltage, any current from the voltage source. Okay, the net current flow out of the circuit here turns out to be 0. That's interesting. But delta V in 2 is going to be delta V32 minus delta V2. Delta V32 is going to be basically minus delta IN over 2 times 1 over GM3. It's going to go down to let more current flow in here. And the voltage we're subtracting off there is going to be minus minus since we're pulling current out of this node, it's going to go down, so it's going to be negative. Delta IN over 2GS1. And so we're going to get delta IN, and we're going to have a 1/2 here, and we're going to have a 1 over GS1 minus 1 over GM3 and so the total delta V in is delta V in 1 plus delta V in 2, which is going to be delta I in times 1 over GM3 plus 1 over 2 GM, or rather GS1 minus 1 over 2 GM3, and so that's equal to delta I in over 2 times 1 over GM3 plus 1 over GS1. And so Rn is equal to delta Vn over delta In. It's equal to 1/2 of 1 over GM3 plus 1 over GS1. Okay, so that, it turns out, is going to be, it's on the order of the 1 over GS of the transistor. And so RO is going to be on the order of much less than that. And so we don't need it there. Okay? And basically what it amounts to is kind of going around the circuit and saying, if I inject a current onto each node in the circuit above and below, is the voltage going to move by something on the order of the delta I that I'm injecting times RO that I'm considering? And if it's going to be much less than that, like it's being set by the transconductance of a circuit, or of a transistor, or the GS of a transistor that is carrying the same current, then probably the RO is going to be insignificant. That's kind of the flavor that this calculation has. Okay, so you don't want to have to go through this explicitly for every transistor in the circuit. What you'd like to do is be able to sort of make that judgment without having to do the calculation. So, for example, if I were to not go through this explicitly, for M2, but if I think about RO2 here, well, if I inject my current here, I'm injecting onto this common source node. So the impedance of this node is going to be on the order of 1 over 2 GSN, like 1 over 2 GS2 or 1 over 2 GS1, because we're looking at the parallel combination of the two source conductances. And that's a much lower impedance than RO2. If I inject onto this node, the output is being held fixed by a voltage source. Voltage isn't going to move at all. And so I don't need the RO2. If I consider RO3, well, if I inject on this side, I'm injecting into an ideal voltage source, VDD. Voltage isn't going to move. It's not going to move at all. If I inject here, I'm injecting into a diode-connected transistor. The impedance that I see of this node is basically 1 over GM3. And so because GM3RO3, the intrinsic gain of M3, is much bigger than 1, I don't need to add the RO3 because 1 over GM3 is a much smaller resistance than RO3. When we move on to M4, consider RO4. Well, if I inject onto this side, the drain side, the source side of M4, again, I'm injecting onto VDD. The voltage isn't going to move. Change in voltage is 0. If I inject onto the drain side, the drain is being held fixed by the ideal voltage source. It's not going to move either. And so the voltage across the transistor isn't going to change as I inject current onto that port. And so I don't need the RO4. Okay, that's the basic idea. Now when it comes time to do the R out part of the calculation, the game is a little bit different. So we're doing the R out part of the calculation. Formally what we are doing is we are saying we're injecting a delta I out, and we want to know what is the delta V out that results. So R out is equal to delta V out over delta I out. And this is the stimulus, or this is the input, and this is the output of our transfer function. And so this, strictly speaking, is the condition under which we are doing the calculation. Okay, so when it comes time to actually inject our test current here, when we split the source and inject onto the VDD side, of course, we're going to get the same thing. Nothing happens, right? Still injecting current into an ideal voltage source. The voltage isn't going to change across the transistor. But when I suck current out of the drain side, now all of a sudden, I'm pulling current out of a pair of drains of ideal transistors that are not being held fixed by the voltage source. And so I would get basically for a finite delta I would get, or for non-zero delta I would get a very large movement of voltage here. I don't get something that's proportional to delta I. And so I would have an infinite incremental impedance here. And so I would need to put in the RO, because that is going to be much larger than the RO. Same thing if I were to inject my current here. On this side, I'm talking to the source of these transistors, very low impedance node. But when I talk to the drain, I'm going to get a very large voltage change. Okay? So I would decide I need the RO2 and the RO4 for this phase of the calculation, but not for the GM phase, because the output voltage is being held fixed. Okay, so that's the heuristic that I use when I go through a circuit and try to decide where to account for the early effect. Hopefully that made some sense. It's the kind of thing where it's a heuristic. I haven't proven to you that if the necessary conditions or sufficient conditions for the early effect being negligible are X, Y, and Z. This is just a kind of a rule of thumb kind of thing that I think most experienced circuit designers and analyzers sort of intuitively use when they're deciding how much detail they need to include in their model to keep the calculation manageable, but to get an accurate model of the situation. Okay, so that's all for this segment. So we'll see you next time.